Even though I'm not an engineer, I learned from engineers that it's very important to be able to calculate real things. Don't make wild scenarios because you're not in Hollywood. You're trying to describe the real world. And engineers are very pragmatic. They're not interested in the theory because it's beautiful. They like it because it works.
2017 की बात है जब मैं भी अपनी बीएससी कर ही रहा था और मतलब नई नई चीजें आपको सीखने का मन करता है। फिजिक्स के आप स्टूडेंट होते हैं तो आपको मन करता है कि आप नई नई चीजें यूट्यूब से कहीं सीख कर कोई किताब पढ़कर कुछ करके ऐसे सीखते हैं। तो एक कुछ वीडियोस हैं जो येल यूनिवर्सिटी की हैं, आप में से कई लोगों ने देखी होंगी। एक टीचर हैं जो पढ़ाते हैं, पूरी फिजिक्स उन्होंने पढ़ाई है। चाहे अगर हम भारतीय भाषा में कहें तो 11वीं 12वीं दोनों की फिजिक्स उन्होंने पढ़ाई है। स्पेशल थ्योरी ऑफ रिलेटिविटी भी पढ़ाई है, मतलब काफी सारी चीजें, पूरी पूरी फिजिक्स उन्होंने लेक्चर्स में खत्म करी है। तो वो वीडियो शायद आप लोगों ने देखी होगी। और वो जो वीडियोस हैं उसमें जो व्यक्ति हैं जो पढ़ा रहे हैं वो और कोई नहीं, हमारे डॉक्टर आर शंकर हैं। तब से भाई मैंने सोचा था कि मैं एक दिन तो इनके साथ बैठ के इंटरव्यू करूंगा, और आज मुझे जाके वो मौका मिला है। और रोजेंडर टॉक्स पर डॉक्टर आर शंकर आज हमारे साथ हैं। डॉक्टर शंकर, आपका बहुत बहुत स्वागत है। और कैसे हैं आप?
ठीक है जी, शुक्रिया।
We can use a little English, so that's not at all a problem. So it's very nice to have you on the podcast. And let's start with your research part, which is our part one. So let's start with that, sir. So, sir, your research interest includes like condensed matter physics. So please tell us something about your research in condensed matter physics. And you have transition from particle physics to condensed matter. So how
Yes,
was that transition for you?
right. So, I was IIT student. I got
Yes.
my degree in engineering.
जी जी जी।
Uh, in the middle, I wanted to leave and do physics. That's because of my brother Rajaram came to India and he was talking to me. Then he asked me some questions. One question was, why doesn't the satellite fall on your head? Why does it keep? And I said it's because it's trying to fall on you, but the Earth is also falling below that at the same rate, so it doesn't get any closer. Somehow he liked that answer a lot. He said, you will be good in physics. Why don't you learn physics? Then he went back to Cornell and sent me this 2 volumes by Feynman lectures on physics. I started reading them, and then I decided this is what I want to do. But my father told me, finish, finish what you started. And after 5 years, you still want to do physics, I will support. So that's what I did. So I had to learn some things myself. But there's another very good physicist called Rajaram Nityananda. He was at IIT with me. And he taught me most of the things I learned. He and I would go for long walks, and during the walk, he will describe each day some topic. I will just listen to him, try to imagine in my mind, then go back to my room and write down some notes. I slip it under this door. He was also an IIT, but he was an MSc program. So I wrote notes every night and said, this is what I think you said. Do you agree or not? And then we'll discuss that. So that's how I learned my subject. Then I took the GRE and I got into Berkeley. And yes, one of the professors who wrote recommendation letters for me is again Rajaram. He had to be very careful because he's my brother. And he explained the very first sentence, this fellow is my brother, but I know him well and I know the American system well, so I should give my input. He wrote for me. Then I got into Berkeley. Then when I went to Berkeley, I said, if I'm not going to be an engineer and do useful things, I want to do the most useless thing in the world. So I asked everybody, what's the most useless discipline? They said, definitely particle physics. That's how I got my thing in particle physics. By useless, I meant with very little connection to daily life. Whereas in engineering, everything is connected to daily life. Whereas in particle physics, it's very remote. So I joined that and I got into that field. Uh, Then when I finished my PhD, I went to Harvard and spent 3 years. Then there I learned another kind of particle physics. There were two rival groups at that time. One group is called the S matrix theory. Other group is called quantum field theory. So I was from the S matrix theory because my advisor, Jeffrey Chu, was one of the founders of that. But I couldn't understand many things in S matrix. I was very confused. That was a good thing because when I went to Harvard, I immediately changed to learn quantum field theory, which turned out in the end to be the right thing to do because now that's what everybody uses. So I did that. Then I went to Yale, and
So,
during that
sir,
time, yeah,
let me just interrupt you here,
please
and
do. Look,
I
you're in charge here. Yes.
okay. I want to put two questions here. As you said, you there were two groups as matrix theory and quantum field. So please explain both of these in your further explanation. That what are these two? Some people have heard about the quantum field theory, but S matrix is something which many of us don't know. Many of us by that I mean कि जो जनरल ऑडियंस है उनको ज्यादा नहीं पता है. जो लोग पीएचडी वगैरह कर रहे हैं उनको थोड़ा बहुत पता है, बट दिस इज सो जनरल ऑडियंस के लिए भी
इन दोनों में फर्क क्या है? So S matrix theory, look, the goal for both theories is to understand physics of particles,
जी
protons, neutrons, how they collide, how they combine to form more objects. So there were the old-fashioned way to do any physics problem. Take the fundamental particles, understand what forces act between them, then solve a mathematical equation, and then find all the things they can do. For example, if you take the proton and the electron, the theory will tell you they will form the hydrogen atom. They will have different energy levels and different probabilities. You can calculate all of that. So they said, let's do the same thing with particles. The only trouble was in the hydrogen atom, everybody knows the proton and the electron are the fundamental parts. And the hydrogen atom is the composite of these two. It's not fundamental, it's built out of these parts. But by the time you went into pions and protons and neutrons, there was a confusion because it was not clear who is fundamental and who is not fundamental. That's the reason is this. Suppose you take two particles of mass m, you combine them, you'll get a particle of mass 2m. And everybody will agree the 2m guy is not fundamental and the little guys with mass m are fundamental. But it turns out when two masses meet and there's a lot of attraction between them, the mass will not be 2m but less than 2m. And it can come down all the way to m. And we got three objects with the same mass, the two things you put in and the stuff that came out. Who is to say what is fundamental? It's not clear. That happens only when forces are very strong. That doesn't happen with electromagnetic forces. So in the hydrogen atom, there is no question what the parts are, but in particle physics, it was not clear where to begin. You don't know where to begin, you don't know how to solve the problem. So the S matrix theory says that we will not ask what anything is made of. We will focus on what is called the scattering matrix. In any experiment, what do? You send two things together, they collide, and maybe two things will come out or four things will come out, different things can happen. And the role of the theory is to give the probability that this will happen or that will happen or something will happen. If you know the microscopic forces, you can calculate this. But you don't even know how to begin this problem because you don't know what the particles, fundamental particles are. But there are some things which are true without knowing the details. For example, we don't know what the probability is that this will happen or that will happen or something will happen, but we know if you add all the probabilities, you have to get one because something has to happen. So that is one property of the S matrix. There are other such properties. And the hope of my advisor was with enough known properties, we can calculate this S matrix, which is the likelihood that if something comes in, something will come out without knowing what the fundamental particles are. So that's a very tricky thing. It's not the way we learn to do physics. So I was not very good at it, but my advisor was a very tolerant man. He said, that's okay, you got some potential. So he got me this good job at Harvard. But as soon as I went there, I went into quantum field theory, which is the second way to do it. Second way to do this is really the older way of doing physics. But you have to know who the fundamental particles are. It's not the pion, it's not the proton, but suddenly they found out in Stanford there are more fundamental things called quarks. And quarks are not like all the others, they are more basic because you can build everything out of quarks. And the collisions in Stanford showed there are some types of quarks, they have so much charge, so many properties. So we knew in terms of what objects we should describe the world. That's the first thing. Who are the fundamental guys? Then the next thing is what's the force between them? Well, it can be any force you want, but it turns out the force between quarks is a very unusual property. The closer they are, the less they interact. We have not seen any force like that. Every other known force gets stronger at short distances. But this force becomes weak at short distances, so that the quarks inside the proton, which are very close, hardly interact. You can tell from experiments. But if you try to rip them apart, the force becomes so strong you can never pull them out. That's why you don't see the quarks. Question is there a theory that can describe this unusual property of strong at long distances and weak at short distances? It turns out there is one theory only. That's called Yang-Mills theory. So that was discovered by David Politzer at Harvard and Gross and Wilczek at Princeton around the same time. That suddenly opened the floodgates because everybody knew what the theory is. We know what the particles are. And as long as the particles are very close to each other, you can do calculations because the forces are weak. So that's the thing I learned. When I went to Harvard, I learned quantum field theory. Then I found this way of doing stuff, you can do a lot of problems. Whereas the S-matrix theory, you couldn't do very many things. It was not really an art. It's more like, not a science, more like an art, guessing the answer. This is more like what we learn in college, how to solve the problem. So I learned that. Then near the end of my stay at Harvard, I collaborated with another physicist called Witten, and he was already a rising star, and he said, somebody in Russia, Zamolodchikov, says that in 2 dimensions, not 4 dimensions, one space, one time, you can actually find the S matrix just by general principles without putting any underlying forces. In other words, in 2 dimensions, the general properties are enough to nail down the function. So he gave me an example and he said, you're the S matrix expert, why don't we collaborate on finding new S matrices? So I learned that it turns out that that problem was connected to something in statistical mechanics. So when I went to Yale, after some time, I left particle physics and moved to statistical mechanics. That, as you said, is one of the founders was Gibbs, who was our Yale big man on campus. He's one of the big daddies of Yale history and American physics, and he is one of the founders of statistical mechanics. So I started getting into that.
So you have done research in condensed matter physics also. So what was your research in that topic?
Right, very good. So statistical mechanics can be any problem which has so many degrees of freedom, you can describe them statistically. In other words, I may not know exactly what you like, what your friends like, but if you give me 10 million guys of your age, I can make a pretty good guess on what you will like. Because big numbers, you can deal with the averages. So when there are many degrees of freedom, the problem suddenly becomes simpler. With 1 or 2 degrees of freedom, it's good. 5 or 6 degrees of freedom will kill you. But if you've got very large number of degrees of freedom, you can apply statistical methods. That's the philosophy of statistical mechanics. You can apply it to any discipline. And condensed matter physics, which I learned after we hired 2 new guys at Yale. One was Subir Sachdev and one was Nick Reed. They were more into condensed matter physics, and they were my young colleagues. And by talking to them, I got interested in that way of doing it. That is the physics of low energy. No colliders, no particles. Every particle is known. In condensed matter, we know what everything is made of. Made of protons, neutrons, and electrons. You don't need anything. In fact, you don't even have to know about protons and neutrons. You have to know there's a nucleus with some charge, and you have to know there are electrons. Then you put them together, You can make a solid, you can make a liquid, you can have a gas, you can have very things. And they're all topics of condensed matter. The word condensed refers to the fact that suddenly all the degrees of freedom are doing the same thing. That happens in a superconductor when instead of moving individually, they move collectively. That happens in a superfluid or in a magnet where each atomic magnet, instead of pointing in random directions, suddenly line up at low temperatures. So that's called condensation. Some behavior common to the whole system appears. That was called condensed matter physics. But nowadays, we don't call it that because the subject has gone way beyond that. It's called many body physics. Compared to quantum field theory, which is infinite number of degrees of freedom, this is many bodies, but not infinite. So I got into that field. That again meant educating myself. So my whole life has been changing my interests, becoming a graduate student one more time, going to seminars where everybody knows more than me, and slowly learning the subject. And I should give one advice to people who are thinking of moving to other areas. It looks very bad in the beginning. Everybody knows more than you. But you have something they don't have. You have come from another field. You have seen things they have not seen. You can think of analogies they will not think of. For example, condensed matter people had a very good idea of the Higgs mechanism before the particle physicists found it because it occurs in superconductivity. So people moving from one field to another, sometimes they are slow, but sometimes they have a lot of insight that will never occur to people working on that field full time. So that's what I tried to do, try to find little gaps where I had an advantage over my competition. And always, whatever you learned before is useful. My father would always tell me, don't forget engineering. He said, you learned it, don't forget it. And that's a good advice because even though I'm not an engineer, I learned from engineers that it's very important to be able to calculate real things. Don't make wild scenarios because you're not in Hollywood. You're trying to describe the real world. And engineers are very pragmatic. They're not interested in the theory because it's beautiful. They like it because it works. And that has been part of my sense of values, even in my new life. I try to do things with some bearing on the real world. So that's how I changed into condensed matter physics. And these problems, like quantum Hall effect or topological insulators, they are all topics in condensed matter physics.
Oh, okay, okay, okay. So
I should mention one thing. When I was writing my paper, suddenly somebody asked me a question. And I said, I don't know what you mean. I never wrote this paper. They said, no, your name is here, R Shankar. Turns out that that's your other guest.
yes,
So
and
he was
he
writing papers in the same field. And when I moved to another field, he had also moved to the same field. So for a while, I was trying to clarify this misunderstanding. Then I said, you know what? He's such a good guy. I don't want to clarify this misunderstanding. Let everybody think I wrote it. So, and if the question is very hard, I would say I didn't write the paper. Ask the other guy.
I should have probably asked him for today to join this meeting and clarify.
I went to IMSC, and for 1 week we both tried to write some papers so we could put our names in the same paper to let the world know there is two of us. But we didn't get enough ideas during the short trip.
जी. Probably you'll get a chance. Not probably you'll get a chance to come together on my podcast and can tell people that there are two,
I
not
think
one.
it's now known there are two because I'm not that active and he's still very active, but he's more into climate nowadays.
He's in climate and many other things like population modeling and other stuff. So he's
Well, I'll
doing.
add to there's one more confusion. I've written many papers. My old student called Murthy, and my namesake also writes papers with a guy called Murthy. He has the same name and same collaborator's name. So,
Name confusion is very
with
very
1 billion Indians, you will think you will have so many different names, but we have same name and same name of collaborators. So,
जी. Well, that like I got confused and I approached both of you. So
Mhm.
in coming time, I'm like thinking that somebody will definitely get into this and will ask that why am I stuck with these two names?
Yeah.
But it would be great to have both of you on on our podcast.